So in this video, we're going to learn some problem-solving strategies. So in chemistry, we do a lot of solving of problems. And that's not just an important skill for helping us to understand chemistry better and more deeply by trying to apply it to new situations, but problem solving is really a skill that you can use in all kinds of diverse settings. And just like being an athlete, if it's something that you train for, little by little, you'll get better at it. And problem solving is one of those really valuable skills that employers in any field really value. Whether you're going to go on to be a doctor, a dentist, a researcher, a health trainer, any noble profession, you're going to need to solve problems. So let's think a little bit about what problem solving is. What is problem solving? Well, here are a couple of definitions that I think are useful. So when there is a gap between where you are and where you want to be, and you don't know how to bridge the gap, well, you've got a problem. So like this gentleman here, maybe he wants to be somewhere else and, well, doesn't know how to do it. Anyway, if you know how to bridge the gap, so if there's still a gap between where you are and where you want to be, and you know how to bridge the gap, then you don't have a problem. What you have is an exercise. You just need to do what you know how to do. Now maybe you'll fail at it because you didn't do it well, but you know how to do it. You just have to execute it. So like our little friend here, who's walking across this rope bridge a little bit precariously. Another way of thinking about it is problem solving is what you do when you don't know what to do. And that's a really hard place to be in. So problem solving, real problem solving, is challenging. And real problems in science take lots of people thinking about it, being innovative, and working hard on these issues, and trying all kinds of different strategies. But problem solving is something that you can begin to be a little bit better at by practicing. So problem solving is a very important skill, but it's very challenging. But it's also very fun and exciting. This is where the real creativity comes in science. So you got to wrestle with these problems because sometimes they fight back. So let's think about some strategies for problem solving. Well, the first problem solving strategy when you have a problem is make sure you understand what the problem is. Now most of the time in this class you'll be given a problem and you'll have to read it. So it'll be kind of a word problem. So you'll want to read the question and maybe reread it, maybe read it again, maybe reread it again. Then try to restate the question in your own words. If you can do that, then you probably understood what the question is about. So make sure that you can clearly identify what it is the question is asking. What's the answer going to look like? Is it going to be a decision about something? Is it going to be a number? Is it going to be a statement? What is it going to be? And if it happens to be a number, we've seen that most numbers also carry a label, so you need to know what that label is. So what are the units that are going to be associated with the number? Write all that stuff down so that you have a really clear grasp on what it is that you're aiming towards. So if you don't know where you're going, chances are you're not going to get there. Another really good strategy that most expert problem solvers use, besides trying to restate the question in their own words, is using pictures, some sort of visual representation, like a diagram, sometimes a flow chart, maybe some sort of map, but it's just some way for them to think about the information that they're given, think about what they don't know, think about where they're trying to go, and trying to get some sense of how to put those pieces together. So this is really something that you should try on every problem that you solve, but particularly any time that you're feeling stuck. Think to yourself, okay, what kind of picture could I draw to help me understand this? So try to draw a picture. Your textbook uses a strategy called COAST. That's an acronym for the first two steps, collect and organize. So what you want to do here is try to identify all the key concepts, the skills that you might need, and assemble any information that you might need. So after you've thought a little bit about the problem, think, okay, maybe you want to know, well, what section of the textbook does this kind of problem relate to? What chemical principles or concepts will I need to know? Definition of density, definition of vapor pressure, how to calculate this quantity, the units on this, a conversion factor between calories and joules. Anything that you think you might need, begin to identify those. So if you can begin to do that, that'll take you a long way to solving the problem. So now you've got these pieces. So now what you want to do is try and organize those pieces. So put them into groups, write down the stuff that you know from the problem, and think about how those pieces might all fit together to lead you to the answer. The next step, A in the COAST acronym, for analyze, is probably the most challenging. So usually you can figure out the concepts that are involved or what section of the textbook might have the material related to what your problem is. And oftentimes you can identify missing information that you might need to know. But what's tricky is how to put all those pieces together to get from all that stuff to the answer. So this is where the real creativity comes in. So it says evaluate the information. Look for relationships and connections. So maybe you can see some things have similar units, a connection between units. Oh, I can use that like a conversion factor. That's often the case, that you can just do dimensional analysis to find the answer to a problem. So sometimes units will help identify the steps that you need to solve the problem. Sometimes I try working backwards from the answer. So I think this way. Okay, what would I need to get directly to the answer? So maybe I have an equation for density, and I know that if I have mass and if I have volume, I can calculate density. So if you can think of an equation or what numbers you would actually need to know to get the answer to that problem, start there. And then work backwards thinking, okay, how could I get this piece of information that I need, mass, let's say, from the information that I was given? Is there any way that I could do that? So that's a way of kind of breaking the problem down into smaller problems, and by starting with the answer and working backwards, you know that you might be able to connect what you have to the answer at the end. Finally, once you've done that hard work of analyzing, then it's about solving the problem. So go ahead, perform the calculation, make sure that all of your units cancel, make sure that you've done whatever you need to do to solve the problem. So go ahead and get the result. Then after you have the result, you're not quite done. So the last part of the acronym, T, is to think about it. So does your answer make sense? I've had questions on exams where I've asked people to calculate the radius of an atom in meters, and when they're done with that answer, they come up with an answer that looks like 1.36 times 10 to the 12th meters. Well, 10 to the 12th meters is pretty big for an atom, right? These are supposed to be tiny things. So check and make sure that your answer makes sense. If it doesn't, then you know you've done something wrong. So also check that the units are correct. So this step right here, analyzing and solving, sometimes you have to do these over and over. So my advice is to try something. Once you try something and you think about it, does it make sense? Well, if it doesn't, go back, reanalyze the bits again, think about, did you miss something? And each time you do that, trying something, thinking about it, deciding it doesn't work, you'll know more about the problem and you'll get closer to being able to solve it. So let's apply this with an example problem. So this is sample problem 1.3 in your textbook. So it says we've got a nugget of shiny yellow mineral, and it has a mass of 30.01 grams. So I guess we place this little nugget on a balance somewhere. Its volume is determined by placing it in a 100 ml graduated cylinder containing 56.3 milliliters of water. The volume after the nugget is added is 62.6 milliliters. Is the nugget made of gold? Wow, that last question seems to come out of nowhere. Seems like there's no way there's enough information in this problem to answer that question. Okay, so yet we've got to figure it out. So what is the question asking for? It's asking for, is the nugget made of gold? Now it doesn't really tell us, does it mean part of it's gold and part of it's not? So I think we should assume maybe they're asking, is it all gold? 100% pure gold. So is the nugget made of gold? So you see, that's a place where we kind of had to clarify the question in our own minds. So we have to think about what information are we given. So we're given some information about mass. We're told that it is shiny and yellow. That's a good sign because we know that's a property of gold, right? It's shiny and yellow. But is that sufficient to mean that it's gold? Are there maybe other things that are shiny and yellow, like a spray painted lemon? I don't know. Maybe. So it probably wouldn't be a nugget so much there. Anyway. But let's see, we're given some other information. We're told its mass, and we're told something about its volume is determined. But then they don't tell us what its volume is. They say we put it in a graduated cylinder that has some water, and they tell us the volume after the nugget is dropped in is something else. So neither of those volumes, I'm guessing, is the volume of the nugget. So we need to think about that. So now we've read the question, we've thought about a little bit about where we're going, so we need to come up with some way of determining whether or not the nugget is made of gold 100%. So that's where we're going. So first step, collect and organize. So all that stuff that I just said, we're now going to sort of group it together. So we're going to write down all this stuff. So we know that we can identify substances by their properties. So gold is going to have a list of properties. For this nugget to be gold, it has to have all those properties that we know gold can expect. So shiny and yellow is one of those properties, but it maybe is not enough. So what properties might be relevant here? So thinking about the information that we've given something about mass and they're talking about volume, we say, aha! I know we've been learning about density. So density is an intensive property, and its formula is given by this equation, density equals mass over volume. So I've collected some information here. So I know that if a material is really gold, it should have the same density as gold. As soon as I find one property that this material does not have that gold has, I know it's not gold. Now it could be it has many properties that are the same as gold, and until I've sort of listed them all, I'm not really sure that it's not 100% gold. So I know the mass is 30.01, but not the volume of the nugget. So how am I going to figure out the volume of this nugget? Well, maybe I need to draw a picture of what's happening. So here's my picture. Now these aren't exactly the right volumes, but because I grabbed this picture off the internet, but you get the idea. So I initially got a graduated cylinder with a certain amount of liquid in it. And then I drop this nugget in. So what's that nugget going to do? It's going to sink to the bottom. Hopefully it doesn't dissolve or anything weird like that. And it's going to push some of the water out of the way. We call that displacement. So we assume then that the picture suggests that the volume of the nugget down here is going to be exactly equal to the volume change that we see in this graduated cylinder, because we haven't gotten rid of any of the water as long as none of it splashed out, and we've got this nugget here. So it's going to be equal to the volume of water displaced. So we could figure that out just by subtracting the final volume from the initial volume. So if we take this minus this, that'll tell you by how much the volume changed, and that ought to be that chunk of stuff right there. So that volume and that volume. Once you take that volume out, it should go back to there, right? And last, we're going to need this piece of information since we think we're going to use density as this property, and we know we can identify substances by their property. We need to know the density of gold. It wasn't given to us in our problem. Well, that doesn't mean all is lost. We're smart people. We know how to find information, right? So we go to some reliable source, and like the CRC Handbook of Chemistry and Physics, and we look up the density of gold. So there it is, 19.3 grams per milliliter. So I told you that analyzing was the hard part, but we've sort of done a lot of the analyzing in the last part of that question, so now it's actually not too hard. So we know we need to use the initial and final volumes of this graduated cylinder to calculate the volume of water displaced. Whatever volume that is, we're going to assume that's the volume of the nugget. Then we can go, and this is where we get to that working backwards question. So if I'm trying to calculate density, what do I need to know? Mass and volume. Can I find those from the information given? Well, I was given mass directly. Using this other information, then I can find volume. So that's that working backwards technique. Didn't really use it here, but that's an example of how it might work. So density is equal to mass divided by volume. We know the mass. We now know the volume here by displacement. So what we're going to do is calculate that, compare the calculated density then to the known density of gold, and to determine if the nugget might be gold, right? So if its density agrees, then it might be gold. It has at least a couple properties. So now we're to solve. So let's do that. So we subtract these two numbers. Following our rules for significant figures, we're going to keep the smallest number of decimal places, and that's 1. So that's 6.3 milliliters of volume. Now density is mass divided by volume, so 30.01 divided by 6.3. That equals this number of grams per milliliter. We've got 2 significant figures in our volume, 4 significant figures in our mass, so we're going to only report this number to 2 significant figures. So my first uncertain digit is right here, and that's because my first uncertain digit in volume was in the tenths place. So I only have 2 significant figures. So 4.8 grams per milliliter. So that is way less than 19.3 grams per milliliter. So this property of this nugget does not match what gold has, so it can't be pure gold. So now let's think about it, just to make sure. So we know that gold is pretty dense, right? You always see these movies where they're robbing a bank or something and lifting these really heavy gold bars out, and they look like they're working hard. Anyway, so a small volume of gold is still rather heavy. The volume of a nugget by displacement is 6.3 milliliters, and in round numbers, okay, we'll just say that's about 6. So the density of gold, 19.3, we're just going to round that up and say, okay, it's about 20, in round numbers. That's just so we can do a kind of back-of-the-envelope calculation here to kind of estimate. So if we had a 6 mil sample of pure gold, how much would it weigh? What would its mass be? Well, it would have a mass of 6 times 20. That's something we can do in our head. That's why I rounded the numbers up. About 120 grams we'd expect to have. But in our question, we only had 30 grams. All right, so that's way less. So that's way more. 120 grams is way more than we had. So again, it seems unlikely that the nugget is pure gold. So I sort of thought about it by looking at the problem in a different way and just seeing how the numbers worked out. And it's too bad that it ain't pure gold, isn't it? All right, so there's an example of how we apply the coast strategy and our problem-solving strategy. Now, many problems that you encounter will be more complicated than this, but this is a good stepping stone problem. So as we go through problems in class and other places, I'll try to use this method and point out problem-solving strategies so that as we go along through the semester, we can practice these things. All right, good luck problem-solving, and enjoy the challenge.